to start the recording?
Oh, okay.
All right. So in the last lecture, you looked at how to find out the loop gain, the total loop gain, which is A times beta in any non-ideal op-amp configuration. So of course, what non-ideality can mean is that you have a finite input impedance, you have a non-zero output impedance, and you have a finite gain. And we looked at methods to take care of all of those, how to find out the loop gain. And depending on the loop gain, what would be the closed loop overall transfer function of the system. And you already know that that is going to be A infinity divided by 1 plus 1 over t. So for homework 2 as well as homework 3, this formula is going to be the most important one. Numerator is A infinity, where you assume your op-amp to be ideal, completely ideal, having an infinite gain, infinite input impedance, and zero output impedance. On the other hand, the denominator has all the non-idealities. The denominator has your loop gain, which is t, and t is equal to A times beta, where beta is your feedback factor. And all the non-idealities related to your finite input impedance and non-zero output impedance is factored inside beta. Okay. So remember that this is going to be the most important equation for both your homework 2 and homework 3. And of course, in future, whenever you're dealing with any non-ideal op-amp, that's the equation that you're going to use in any kind of analysis. You have looked into examples of how to find out the total loop gain T, which is A times beta, and beta as a factor of, for example, these multiple voltage divisions, right? So again, start from the dependent voltage sources output, figure out what would be the voltage divisions happening along the way as you traverse back toward the input. And remember, you are always trying to figure out what is the voltage that is fed back at the input of the op-amp. So between the positive and negative terminal or inverting and non-inverting terminal of the op-amp, which is basically where this input resistance of the op-amp is sitting, right? So you're eventually trying to find out what is the voltage drop across this input resistance of the op-amp. So just work your way backward from the output of the dependent voltage source back toward the input side. And that should give you the ratio, the voltage division ratios, which will eventually become your beta factor. Okay. And beta times A is going to be your T or loop gain. All right, so we looked into a few examples. We'll take a look at a few more examples in today's lecture. But in the last class, we were also looking into how to find out input and output resistances. And as you know, that finding out output resistance means find your Thevenin equivalent resistance at the output port. Finding input resistance, that means finding out the equivalent Thevenin resistance at the input port. And for that, of course, first thing you need to do is to kill all the independent sources. That means short all the voltage sources, independent voltage sources, and open all the independent current sources. Put a test voltage source or test current source, whatever you are more comfortable with. Find out the other quantity. So for example, if you're putting a test voltage source, find out the current that is coming out of the test voltage source. And the ratio of voltage to current, according to Ohm's law, will give you the resistance. Right? So, and that's the same approach that you should follow while finding input-output resistances or resistances at any point in the circuit or in the system. We looked at a few examples. Few of them could be very intuitive. So for example, no current goes into the op-amp. So of course, resistance looking into any of the terminals of the op-amp, let's input terminals of the op-amp, that will be infinite, of course. The output resistance, if you're looking into the op-amp's output, you know that there is going to be a path through the op-amp's output connecting you to ground because there is a dependent voltage source connected at the output of the op-amp. That's the model of the op-amp, right? And you know, for a dependent voltage source, if that is ideal, that is going to present just a zero resistance. And that's why when you're looking into the output of the op-amp, there's always a zero resistance path to ground. So whatever comes in parallel to zero, overall you'll still have a zero resistance. All right, so, but be careful about certain scenarios. For example, over here, as you see, that because this is a negative feedback, you will have a virtual ground property, which means that if your non-inverting terminal of the op-amp is connected to AC ground, the inverting terminal is also at AC ground, right? Now, as you are trying to find out what is the effective resistance between the two input terminals, that is going to be R1 in this case, because you already have an AC ground at both of these points. Similarly, in this case, your input Rin at this particular port in between these two terminals, your Rin is going to be 0. Because again, remember that this point is a virtual ground. This point is also a virtual ground. So the resistance between two virtual grounds is going to be 0. Now, we were looking into a few different examples for non-inverting op-amps, voltage followers. Then we looked into inverting amplifier, summing amplifier, I2V converter in the last lecture. One thing that we did not look into in detail was a current mode output. So basically, if you have a voltage input, so you have a voltage source at your input, but you're trying to find out what is the current going through the ZL resistance at the output. And again, it's just that this is one particular configuration, how the resistors are connected for the op-amp. You can have many other configurations, right? We already know that you can have hundreds of different configurations with an op-amp in between, and then many types of feedback connected around it. So let's just take this example and try to find out what is going to be your output resistance here. Of course, input resistance at this particular terminal is going to be 0, because if you place a voltage source over here, no current will go into the op-amp, inside the op-amp. So basically the resistance that we'll see at that particular terminal is going to be infinitely large. However, what is going to be the R out in this case? So let's just think about it for a moment. And this is going to be something different from whatever you have seen before, right? So if you're trying to find out the output resistance at the output, so basically just keep in mind that your output is a current in this case, and you're trying to find out if you put a test voltage source at the output, how much current will flow through this output path. So basically this is the ZL resistance, and the current through that ZL resistance is going to be your I out, right? So first thing that you need to do to find that out is to remove the effect of any independent voltage or current source. So let's just short out this independent voltage source at the input. And then you're going to put a test voltage source over here, which let's call it Vx. Okay. Now what you're interested in eventually is that at the output, this is the resistance through which you are calculating your output current, IO, or output current through this ZL resistance, right? But as you have connected this Vx source at this node, what would happen to the current that is coming out of Vx? There is a current that is coming out of Vx, and all of that current is going to flow into the op-amp if this op-amp is ideal. If the op-amp is ideal, all of that current will flow into the op-amp and go to ground, because the output resistance of the ideal op-amp is 0. So there will be no current going through the ZL resistance. So there will be no current. Let me draw it with a different color. So this path will actually have no current flowing through it. So if you're considering your output as the current flowing through the ZL resistance, there will be 0 current at your output, right? And if there is 0 current at your output and you have connected a voltage source Vx over here, the ratio of Vx over 0 current, that's going to be the output resistance at the point where you're considering your output, right? So Vx divided by 0, that's why your R out in this case is infinitely large. Even though the op-amp's output resistance is still 0. The op-amp is an ideal op-amp. The output resistance looking into the op-amp at the output port is still 0. But for this particular system, this particular overall circuit, your output was the current going through ZL, right? So whatever test voltage source that you connect over here, all the current from the test voltage source will go into the op-amp, which is not your output current anyway. Your output current was this, whatever is flowing through ZL. So keep that in mind. And this is where, like even when I was a student, I used to make mistakes that, okay, what is my output quantity, right? You have to be careful about that. The current that is flowing through ZL is your output quantity. So if you're trying to find out the R out of this entire system, you need to make sure that you're considering the current flowing through ZL. And in this case, the current flowing through ZL, if you connect a test voltage source over here, the current flowing through ZL will be equal to 0, because all the current will go through the other path. And that's why the output resistance, if your point of interest or the current of interest is this, then that output resistance corresponding to that is going to be infinite. even though the op-amp itself has a zero output resistance. So always think about what is my system's input and output, not the op-amp's input and output. Op-amp's input is always infinitely large if it is an ideal op-amp. Op-amp's output resistance is always zero if it is an ideal op-amp. So whenever you're asked about R in and R out, you're always asked about the R in and R out of the system, not the op-amp. The op-amp's input and output is trivial. Everybody knows that. So nobody will ask you that as a question. Whenever you're asked that question, it means you're asked to find out the R in and R out of the system and not for the op-amp. Okay, keep that in mind and this will become very easy. All right. Yeah. So what is R? So from Ohm's law, what is resistance? Resistance is the ratio of voltage to current, right? Now, if you connect the output, let's have voltage source at the output. Let's say you're connecting a test voltage source at the output, Vx or V test. You are interested in how much current actually goes through your output, right? From that voltage source. That is your output impedance. So the voltage at your output node divided by the current at your output node, that's your output resistance, right? So what is the voltage at your output node? That's the voltage is over here because this is the path, this is the current that is flowing in your, and this is what you're defining as your output current for the system, right? What is the voltage at that particular path? It's Vx, right? Because this is the point that is connected over here as well. What is the current that is flowing through ZL in this configuration? 0, right? Why? Because all the current is flowing through the other path. The op-amp has a zero output. The op-amp itself has a zero output resistance. That means no current is flowing in this path. And that is the reason why your R out for the system is infinitely large. And the system means whatever you are considering as your input and output. Questions?
So when we do input impedance, like typically we've had a voltage test source.
Yeah.
And we check the current going through it, and then you use Ohm's law to get the input impedance. And the kind of thing we've been looking at is the test voltage source.
Right.
But here we add the voltage source, and then we're looking at the resistor. In general, can we add the test source like anywhere and then just observe the thing that we care about, but we put it here because it was easiest? Or
no. So for example, let's say you want to find out your resistance at a particular node A. Let's just say any node A in the circuit or any node X in the circuit. So you have to put your test voltage source at that particular node, right? For example, here you are interested in the output impedance, given that your output is a current flowing through the ZL race. So you will connect your Vx test voltage source at that output point, right? You're still going to connect it at that output point. Yeah, if you connect your Vx at the input, that will not work because you're trying to find out the output resistance, right? But keep in mind, what is the quantity of interest? Is it a voltage or is it a current? And where am I looking at that voltage or current? Right? So you have to put your test source at exactly that same point where you're interested in finding the resistance. Okay, thanks. All right. So there is also another document uploaded as self-study more loop gain example. So let's look at a few examples from there, and then if there is time remaining, we'll start with the frequency response in today's class. Okay. All right. Also keep in mind that your homework 3 will be due this Friday, this week, and your labs are going to start today, right? So I hope all of you are. All of you know that, and also someone pointed out that the video from last year's TA office hours, it was not accessible to some of you, I presume, or I'm not sure. So I actually changed the format and pasted it as a video over here so that it directly plays. So if I go to the student view, I hope everybody will be able to see that video. So please make sure you watch that video before you go for your lab 1 or submit your lab 1 pre-labs. Okay. So again, let's take a look at a few more examples. Again, all of you should be very familiar with the concepts by now, but this is just to show you a few examples of what we are trying to find out. So for example, this circuit, let's again find out what is my A infinity, what is my R in looking into this port or looking into this terminal, what is my R out over here, and of course, eventually we'd also be interested in beta and the loop gain, right? So first thing is finding out A infinity. For A infinity, you'll assume ideal op-amp conditions. So there's no current going into the op amp. Your current in the positive terminal is 0, current in the negative terminal is 0. And because you have a negative feedback, the voltage at the negative terminal, so let's call it V minus, and the voltage at the positive or the non-inverting terminal, let's call it V plus. So V minus equal to V plus because of the virtual ground property. Right? Now, because your current going into the non-inverting terminal is 0, so there is no current going in, so the voltage at the bottom terminal of R3 will be same as the voltage at the top terminal of R3, right? No current going in. According to Ohm's law, the voltages are equal on the two sides of the resistor. So your V plus is also equal to 0. Even though V plus is not directly connected to ground, because there cannot be any current flowing into that positive terminal of the op amp, the voltages at the bottom terminal of R3 and the top terminal of R3 are going to be equal, according to Ohm's law. So your V plus is going to be 0, which means your V minus is also going to be 0, according to the virtual ground property. Okay. So what that basically means is that there is no effect of this R3 resistance. Now, what is your current flowing through the R1 resistance, which is over here? This is the R1 resistance. So that current is going to be Vs minus this point's voltage, which is V minus. So Vs minus of V minus divided by R1. And again, according to Ohm's law. So that is equal to Vs divided by R1 because your voltage at the inverting terminal of the op amp is 0. Okay. Now again, no current can go into the op amp. So all the current that is flowing through R1 has to flow through R2. So IR2 is equal to IR1. And from there, you can find out what is going to be your output voltage. VO, that is going to be V minus of IR2 times R2. Now V minus is equal to 0. So you have a minus, and then in place of IR2, you're going to put Vs over R1, because Vs over R1 is what you found from here. So you're just replacing IR2 with Vs over R1, and then multiply that with R2. So your A infinity is going to be minus R2 over R1, because A infinity is what? A infinity is VO divided by Vs, assuming that the op amp is ideal. So that is minus R2 over R1, which is equal to minus 2. Again, very simple. You have learned this in 3111. To find out R out, the first thing you need to do is set Vs equal to 0. So you need to get rid of any independent voltage or current sources. So set Vs equal to 0 because you don't want those current or voltage sources to fight with each other. And then you're going to either apply a output test voltage source or a test current source at VO, at the output node, and then find out the other quantity. If you're applying a voltage source, find out the current. If you're applying a current, find out the voltage. In this case, because you're directly looking at the output terminal of the op amp as well, so your VO, which is the output voltage quantity, is over here. So of course your R out eventually, whatever method you apply, your R out is going to be 0 eventually. Right? What about R in? R in is the resistance looking here. And again, of course, you know that you can put a test voltage source at this input point. And because this point is a virtual ground, so all you see is this resistance, which is 10 kilo ohms. So your R in is going to be equal to R1. Your R in is going to be equal to R1, which is equal to 10 kilo ohm. Now the interesting part, where you want to find out T, or the overall loop gain. And to find out the overall loop gain, the factors that you have considered is, let's say your gain of the op amp is 400. The output resistance of the op amp is finite, non-zero, and that is equal to 1K, 1 kilo ohm. And the input impedance of the op amp, which is R in, is equal to 80 kilo ohm. So those are the non-idealities. The op amp does not have an infinite gain. It has a gain of 400, does not have a zero output impedance, has 1 kilo ohm output resistance, and does not have a infinite input impedance. Instead, it has 80 kilo ohm input resistance. Okay, those are the non-idealities. Now you want to find out beta. Again, for that, start from the output node of the dependent voltage source and walk your way backward to the input side. Right? That's what you're going to do. You may also want to, let's say, redraw the circuit in a different way if it seems easier for you. Right? For example, that's the way we have done it here. So the way the circuit has been drawn here, it's the same circuit, but simplified. So instead of this dependent voltage source, so you start from the output node here. Let's call that point Vx. After that, you have this RO, which is this resistance. Okay. Then you have R4 going to ground, which is this resistance here going to ground. And then there is a parallel path, which is 20 kilo ohm, this R2, going back to the input positive terminal over here. So 20 kilo ohm, which is R2, placed here. And at this point, you have one path going towards through R1. So you have R1 going to ground. And there is another path which goes through Ri and R3. So you have Ri and goes to R3. So that's the other path. Okay, so that's basically the equivalence between these two circuits. So it's basically the same circuit, but it helps you think in a more simplified, streamlined manner, because you just put your voltage source over here, redraw the circuit in a way that everything flows in the one direction instead of having feedbacks and trying to think about from output to the input side. You just think from let's say left to right. And with that, eventually what you're interested in is that what factor of this Vx voltage, you start with this Vx voltage, what factor of that Vx voltage is available across Ri. Ri is the input resistance of the op-amp. You are interested in what is the voltage available across that Ri, right? And that factor becomes your feedback factor. So it's exactly same as what we saw in the previous examples. All right. So now let's take a look at the numbers. Your Ri was 80 kilo ohms and R3 was 30 kilo ohms. So if you're looking at the resistance at this point, you basically see a series combination of 80 kilo ohm and 30 kilo ohms. So this is 110 kilo ohms. Okay. At this point, what do you see? You see R1, which is 10 kilo ohms, in parallel with 110 kilo ohms, which is a combination of Ri and R3. So if you call this resistance as Rx, Rx is R1 in parallel with Ri plus R3. So 10 kilo ohm in parallel with 110 kilo ohm. So that is about 9.17 kilo ohms. You can also approximate that as 9.2 kilo ohms. You may also approximate as 9 kilo ohms. And maybe because this is 10 times higher, you may also want to approximate it as 10 kilo ohms as well. Your final numbers will not change much because of that. Question?
In this case, the voltage feedback at the very end ends up with a positive terminal of Ri. So is this a positive feedback system?
Okay, let me check this. So according to, so for example, what you see over here is the output goes back to the negative terminal of the op-amp, right?
The polarity
Yes. Yes, this is a good point. So basically the voltage that you're looking at is over here the way it is drawn, so it has to be the opposite. So this is I can correct this slide and re-upload, but that's a great point that this needs to be the positive terminal and this is the negative terminal if you want to be perfectly, let's say, accurate. So basically this is going to be negative and this is going to be positive. But then again, think about it that, okay, we are looking at the absolute value of the gain here in most cases that you have seen. So the absolute value of the gain does not change. But because it is flipped, you're right that if you want to be exactly accurate, there would be a 180-degree phase shift because of the feedback, right? All right. So you can find out your Rx as a parallel combination of 10 kilo ohm and 110 kilo ohm, which is very close to your 10 kilo ohm. Now, I leave that up to you, how much accurate you want to be. You can be accurate up to 5 decimal digits. You can be accurate up to 1 decimal digit. Everything is fine because your final answer will not change much. So again, as I was speaking to someone from the class yesterday or the last class, that unless you are, for example, designing your circuit for, let's say, landing on Mars, but you actually need to be extremely, extremely accurate, right? There you need to be probably 5 or 10 decimal digit kind of accuracy. But if you're just designing a circuit and maybe that circuit is for let's say, a mobile phone, you may get away with a little bit of inaccuracy, and that's okay, right? You just need to do the design in a fast way because that's what, for example, TI or analog devices, Qualcomm, they're looking for. That okay, you need to do it fast, but certain assumptions are okay, right? You do not need to be accurate up to 5 decimal digits. Okay. So just make sure that you practice in that manner for your interviews, for internships, full-time jobs, and so on. Okay. Similarly, you can find out what is Ry. Ry is going to be this R4 resistance in parallel with R2 plus Rx. You already found out what is Rx, which is about 9.2. And then R2 was 20 kilo. So 20 plus 9.2 is going to be about 29.2. Again, 4 kilo ohm in parallel with 29.2, that's about 3.5 kilo. I think a good rule of thumb is that if the two resistances are, let's say, 10 times apart, you're looking at 1 kilo ohm in parallel with 10 kilo ohm, you can approximate it as 1 kilo. If it is not 10 times apart, just do a little bit of the calculation of how much the parallel resistance is going to be. That's a rule of thumb when you're doing circuit design. Okay, but if you want to be accurate, let's say up to 2 decimal digits, as it has been shown in this particular example, your beta factor eventually is going to be the combination of these 3 voltage divisions. Very similar to what you saw in previous examples, right? So I'm not going through that again. Basically, one voltage division is between Ry and Ro, then the next one is between Rx and R2, and the third one is between Ri and R3. Remember, you're interested in the voltage drop across Ri. So whatever contains that voltage drop, that would be your voltage of or factor of interest. That, for example, for the third component, you're interested in Ri divided by Ri plus R3 because you want to know the voltage drop across Ri. And you know from the first lecture that the voltage drop across a resistance is proportional to the value of that resistance. So you're interested in Ri. For the second term, you're interested in the term that contains Rx because Ri is hidden within Rx. For the third term, you're interested in Ry because eventually Ri and Rx are hidden within Ry. So just make sure that you're looking at the correct voltage divisions as you are solving the problem. Just put the numbers, you find out beta value. Your T, which is the overall loop gain, is going to be 8 times beta. So 400 times this number, which is equal to 71. So overall, you see that you still have a very high loop gain. So T is pretty high, much more than 1, which is the expected condition. Now, your A infinity was -2. And see, this is where your the negative sign that you talked about. So this comes in, that A infinity is -2. So your T was 71. So a closed loop gain is going to be A infinity divided by 1 plus 1 over T. That's 1.97. So again, as you see that for this particular example, it's pretty close, right? Even if you do not consider the non-idealities, you will say that my gain is going to be 2. And if you consider the non-idealities, your gain is 1.97. So you're still pretty close. So for this particular application, it is okay, even if you don't consider the non-idealities. And why did this happen? This happened because of the values of the resistances that are considered. For example, the 80K resistance is pretty high as compared to other resistances in the circuit. The 1K resistance at the output of the op-amp, that's also pretty low as compared to the other resistances, right? But if this would not have been the case, let's say you have a 5K resistance at the output, whereas this is 4K. And instead of 80K, let's say you just have a 10K resistance at the input, right? Then you would see that there would be a major difference as compared to the original A. So maybe just as a homework to understand this better, redo the problem with R in equal to 10 kilo ohm and R out equal to 10 kilo ohm again, right? And you'll see the huge impact that the input and output resistances will have in that case. Questions? So this is your output that so you're starting from this point and you want to find out what is the voltage available at this, like in between these two terminals, right? Across your Ri resistance. So that's the voltage that you're interested in, right? So you want to find out the voltage division of this over your Vx. So as you see, beta is the ratio of those two voltages because you're interested in how much of the input voltage, how much of Vx is finally available across the input terminals of the op-amp. That's the only thing that you're interested in here. And for that, you're doing this voltage division, again, as you learned in previous classes. All right. So let's see one more example, maybe. Yeah, there are a few other examples in this. Let's see which one we want to take a look at. All of them are very similar. So let's take a look at the example for one of them. Let's say part C. So in this case, again, you are asked to find out A infinity. And to find out A infinity, you will assume ideal op-amp condition, right? So your op-amp will have infinite gain, infinite input impedance, and zero output impedance. So there would be no current going into the op-amp. If there is no current going into the op-amp, your V plus, the positive terminal, this terminal's voltage, how much would that be? Right? So your positive terminal's voltage is the voltage at this point, which will be same as the voltage at this point, because no current can go into the op-amp's positive or the non-inverting terminal. The current is equal to zero. If the current is equal to zero, the voltage drop across the resistance is zero, according to Ohm's law, which means that the voltage on the left side of this resistance will be exactly same as the voltage at the right side of this resistance. Okay. So your A infinity, when you're trying to calculate that, because your I plus, the current going into the plus terminal of the op-amp is equal to zero, so that means V plus is going to be equal to Vs. So V plus, which is the voltage over here, is going to be exactly equal to the voltage at the left side of this R3 resistance, which is equal to Vs. Now, again, this is a negative feedback. Your output is getting feedback at the negative terminal of the op-amp. So your V minus is going to be V plus according to virtual ground property. And you already know V plus is equal to Vs. Right? So your V minus is also going to be Vs. Okay? And if you know that, if this point's voltage is equal to Vs and this point's voltage is equal to ground, you know how much current will flow through this resistance R1, again, according to Ohm's law. So IR1, that is the current flowing through R1, will be equal to Vs divided by R1. Right? So that's the current flowing in here. Of course, the current going into the op-amp's negative terminal is also equal to zero, because the op-amp is an ideal op-amp. So I minus is equal to zero, which means that the current that is flowing through R2, all the current is flowing through R1. There is no current going back into the op-amp. So all the current that is flowing through R2 will eventually flow through R1. So this is the path of the current over here. So IR2 is equal to IR1. And you already found out what is IR1. That is going to be your Vs over R1. So if you know that, your VO, that is the voltage at the output terminal, is going to be V minus the voltage at the, let's say, the negative terminals, op-amp's negative terminal, plus the voltage drop across R2. What is the voltage drop across R2? IR2 times R2. The current through the R2 resistance multiplied with the value of the resistance, that is the voltage drop across R2. So the voltage at the output of the op-amp is going to be the voltage at the negative terminal of the op-amp plus whatever voltage drop you have across the R2 resistance. So the negative terminal of the op-amp had a voltage of Vs, and IR2, which is equal to IR1, is equal to Vs over R1. That's what you found out in the previous step. So Vs over R1 is your IR2. That multiplied with R2 is going to give you the voltage at the VO terminal or the output terminal. So what is your A infinity? A infinity is VO divided by Vs. So final output voltage divided by the original input voltage, VO divided by Vs. And as you see, VO is Vs plus R2 over R1 times Vs. So your A infinity, which is VO over Vs, is 1 plus R2 over R1. Now you know the value of R2, which is 20 kilo ohm. You know the value of R1, which is 10 kilo ohms. So 1 plus R2 over R1 is going to be equal to 3. Right? So that's the amount of gain that you expect from this circuit, or the maximum amount of gain that you can expect from this circuit if the op-amp is ideal. Question?
I'm sorry, why don't we look at R4 if we're looking at the output?
Great question. So think about the output. So if you think about Ohm's law again, so you know the voltage at this point, that's a known voltage for you. You know the current flowing through R2, and you know the value of the resistance R2. So that's all you need to find out the voltage at this point. So what R4 does over here is create a parallel current path. So basically there would be a current VO divided by 4 kilo ohm going here, and there would be a current path through this. And of course, there would be a current path going into the op amp, right? So there are 3 current paths over here. So that's all you have from the output side if you connect the output voltage source at the output node, right? So that's why R4, as you see, does not come in picture when you're trying to calculate the voltages and currents at all. Okay? Similarly, for example, in the previous example that you saw, so there was this resistance over here. This does not even come into picture, right? Because this point was ground, this point is also ground because there is no current going in. Right? Okay, so that's about your A infinity. Now, if you want to find out R in and R out, again, I think those will be very easy for this particular example. R in is the resistance that you see at this point. Now, of course, as you look here, right? As you look into this particular direction towards the right at the input node, of course, this is a negative feedback circuit. That means virtual ground property will hold. However, note that this point's voltage is Vs. This point's voltage is also Vs, right? So even though you have a virtual ground property, the value is not actually equal to AC ground. The virtual ground property is there, but you do not have an AC ground at the input, at the non-inverting terminal of the op amp, right? So if you do not have an AC ground, what do you have here? That you have a voltage Vs here, you also have the same voltage Vs at this point. So the current that is flowing in is equal to 0 because the voltages at these 2 terminals, left and right of the resistance R3 is equal. Whatever you do, there will be 0 current. If there is always 0 current, the resistance is going to be infinite, right? So in this case, the Rin is infinitely large. Even though you have a virtual ground property. But remember that virtual ground does not mean and that is why it is called virtual ground. It is not an actual ground. What virtual ground says is that the difference of voltages between your positive and negative terminal is going to be 0. And 0 is ground's voltage, and that's why we call it virtual ground. But in this case, because both your inverting and non-inverting terminal of the op amp has a voltage of Vs, and even though virtual ground property holds true, these are not actual grounds. If this had been an actual ground, then the resistance looking in would have been just the value of this R3 resistance, which you saw in one of the previous examples. But here, because both of the left and right side of R3 resistance is at an equal voltage, whatever you do, the current is always going to be 0. And if the current is always going to be 0, the resistance is always going to be infinite. Right? So some of these concepts might seem a little bit confusing, but think through it. You'll see that it will become very much intuitive. Right? Just what you need to do is just to apply some of these methods that you already know about: virtual ground property, Ohm's law, KCL, and KVL, and the answer will be a combination of that. Okay, finding out R out. So in this case, again, since your output node is this, so R out is generally much easier than finding out R in. So if you see that your output node is directly connected to the output of the op amp, and that's the node, the voltage or current that you're interested in is at that particular node, then of course your output resistance is going to be 0. All right. Now to find out closed loop gain, ACL, what you'd be interested in is to find out A infinity divided by 1 plus 1 over T. And you'll see that the values of these resistances and the way beta is calculated is going to be exactly similar to the previous problem. So you have 10 kilo ohm, 20 kilo ohm. So all these values are exactly same as the problem that you had earlier. Oh, no, this is a little different, but eventually you'll find out that the beta number will be very similar. And then you can find out what is going to be the overall closed loop gain as a function A infinity divided by 1 plus 1 over T. And you'll see that that factor will come out to be, again, very close to the original gain number 3. Okay. All right. So now with this in mind, what we wanted to start today was a discussion on frequency response. And we'll continue these discussions in the next lecture as well. But today I'm going to talk about a little bit about the basics of what you need to know for frequency response. And for that, maybe let's start with the concept that if I have a blank page somewhere, but you can do some math. Yeah. Okay. So let's start with the concept of filters, right? Because you know that a frequency response, what that means is that if you plot the response of your circuit, if you plot your response of your circuit with respect to frequency, and let's say by response of your circuit, what we mean is the transfer function. So the ratio of output quantity over input quantity. Let's say you're eventually interested in that, which is the gain or the transfer function. So if the transfer function is a function of the frequency, right, then only you are interested in frequency response. If the transfer function is always flat, you don't even care, right? Because every frequency is treated in the same manner if the transfer function is flat. Only time that you're interested in the transfer function with respect to frequency is that if there is some kind of a change with respect to frequency. Let's say the transfer function looks like this, that after a certain point, the value of the transfer function or the value of the gain drops. Or it might be a scenario where your gain is low in the beginning, and then after a certain frequency, it starts to rise. You may have a scenario when the transfer function versus frequency looks like this. You may have a scenario when the transfer function versus frequency may look like that. So you have some idea about high pass filter, low pass filter, band pass filters, band stop filters, and so on. So, and as you know that you're only interested in those filters because they are dependent on frequency. So you want to filter out a certain frequency range, you'll go for a band pass filter. You want to get rid of, let's say, the 60 hertz noise coming from the power lines, you generally go for a band stop or a notch filter at 60 hertz so that your circuits are not affected or impacted by the power line interference. You may have a high pass filter or a low pass filter depending on the need of the circuit. So let's just first start with calculating what would be the transfer function if you have a simple circuit containing a resistance and a capacitance. So let's say you have your input connected on the left side. So let me call this V in, or let's just call it Vi, and your output is Vo, right? And I'm writing Vi and Vo because I just don't want to write too many characters right now with my mouse. But so what you're interested in is just the ratio of Vo over Vi, right? And this is resistance R and the capacitance is C. Now in treatable, so when you learned about filters a little bit, you know that we generally consider the resistance as a quantity that is that has an equal value of impedance over all frequencies. Like resistance is just resistance. On the other hand, capacitance or inductance can have impedances, which is frequency dependent. The impedance is just frequency dependent resistance. Okay, and for a resistor, the value of the resistance does not change with frequency. Right? It's flat. On the other hand, the impedance of a capacitor, and many of you know about Laplace transforms or the frequency response of capacitors or inductors. You know that the impedance of a capacitor is 1 upon SC, where S is equal to j omega, and omega is equal to 2 pi times F. So j omega is equal to 2 pi or j times 2 pi times F. And F is your frequency, right? So the impedance of a capacitor reduces with frequency. If you increase your frequency, the impedance of the capacitor will reduce. On the other hand, if you had an inductor, so inductor's value is L, and the impedance of the inductor would have been j omega times L or S times L. So as omega increases or as frequency increases, the impedance of the inductor increases. So for a capacitor, if you're plotting the impedance of the capacitor with respect to frequency, let's just call it impedance Z. For a capacitor, the impedance will fall. For an inductor, the impedance will rise with frequency. And it rises linearly because this is j omega L. So as your frequency increases by 10 times, Z will increase by 10 times and so on. Okay. So that's just the impedance of the capacitor and inductor. Now in this case, because you are interested in VO over VI, that's eventually a voltage division ratio, right? So if you just know the impedance of the capacitor and the impedance of the resistor, you can do a voltage division, right? Just like we learned earlier. So let's say the resistance of the, let me just clear out some of these things. So from now on, let's just say that I have an impedance ZR for the resistance, and I have an impedance of ZC for the capacitor. Right? Now, what would be your voltage division ratio here? VO over VI. That is going to be ZC divided by ZR over ZC. ZR plus ZC. Very simple voltage division that you learned in lecture 1. Now, what is ZC? You already know ZC is 1 over SC. So your numerator is 1 over SC. Your denominator is 1 over SC plus, or basically R plus 1 over SC. Let me write it in the correct fashion. So ZR is equal to R and ZC is equal to 1 over SC. Now you simplify this. Your numerator becomes 1. Your denominator becomes 1 plus SRC. If you want to represent in terms of j omega, you know S is equal to j omega in the Laplace domain, you call it S, but that's just j times omega. So 1 over 1 plus j omega RC. Now what is interesting here, that from your 3111, you also know something about time constants, right? The RC time constants of any resistor capacitor circuit, right? What is the RC time constant here? As you know from the name, RC time constant is just R times C. And the RC time constant is also equal, just from the RC time constant, you can also find out the bandwidth of the system. So the bandwidth of the system is 1 upon RC. Again, many of you are already familiar with the RC time constants and concept of bandwidth. You know that the bandwidth of this system is going to be 1 upon RC. So let's call it omega P. That's the bandwidth, and I'll basically explain why we are calling it omega P, because there will be a pole at the location of the bandwidth. That's why we are calling it omega P. So if that is 1 upon RC, then RC is going to be equal to 1 upon omega P. Right? Now let's go back to this equation. So you had 1 divided by 1 plus j omega RC. So I can write that down as 1 plus j omega divided by omega P. So wherever is my RC time constant, or wherever is the location of my pole, which is equal to 1 upon RC, I can represent the transfer function of this system in this form, 1 divided by 1 plus j omega divided by omega P. Now, also, why do we call it a low-pass filter versus a high-pass filter? You know how to calculate that is, first, you may take a look at a frequency of 0. So if you take omega is equal to 0, in this case, your denominator will become 1 plus 0, which is equal to 1. Your numerator is already 1. So you have a factor of 1 at 0 frequency. At a frequency of omega equal to RC, or omega equal to 1 upon RC, you have 1 divided by 1 plus j, when omega is equal to 1 upon RC. So omega and RC cancels out. So you just have 1 divided by 1 plus j. And as you know from the theory of complex numbers, the magnitude of this is just 1 divided by square root of 2. Right? 1 divided by square root of 2. We'll discuss this in more detail in the next class. But what this means is that that's why you'll have your 3 dB point, because at your 3 dB bandwidth, your signal value reduces to 1 divided by square root 2 times, which is in power form square of this, and that means your half power point. The square of 1 divided by square root of 2, that is equal to half, right? And that's where the half power point comes in. And after this, you'll see that as you increase your frequency, the value of the amplitude will go down. So this will be a low pass filter. So we'll stop here, and in the next lecture, we'll start from this.